Hi, everybody. My name is Serrano. Very happy to be here. And so a really nice introduction to Tejo and team. I'm going to tell you what are transformer models. So I work at Cohere, I'm developer relations lead. And I'm going to tell you basically a very friendly introduction on what are transformer models. So if you know machine learning, neural networks, anything, fantastic. But if you don't, then that's fantastic too. So this works for everybody because we're gonna go from scratch. And I have the chat right here, so please feel free to ask me any questions on the chat or put your microphone and just shout them out. If we go in different directions, that's wonderful. That's fine for you. So anyway, what are transformer models? They are a very cool thing that you may have heard a lot from, like models, like Cohere model, ChatGPT, everything right now. It's a transformer model. And what do? Well, they pretty much generate text. That's what they do. And generating text is not a new thing. We've probably seen it many times. For example, if you use WhatsApp or text messaging or anything, that generates text, right? That generates the next word in a sentence. If you type something like hello, how are, it just recommends 3 words that you can use, and the one in the middle is sort of the one that it mostly recommends. So how are you, how are yours, etc. And the question is how does it generate text? So let's just start from scratch and see how would you fill in the next word in a sentence. So for example, I'm going to ask the crowd, what word would you put here? Hello, how are? What's the next word that you would put? Maybe I put you. Yeah. People say, yeah. Hello, how are you? Yeah. I would say hello, how are you as well. And the question is, how would you make the computer do this, right? If you have 10 minutes to code something quick, how would you make it answer the next word? So there are methods that are basic and there are methods that are more advanced, but let's say what's the most basic thing that you can think of? And so here's one. I just look at one word, okay, just the word are, and then I go in a huge data set. And I look at all the times the word are appears, and then I look at the next word, and the one that appears the most is the one that I'm going to pick. So let's say that there's a bunch of sentences that said something are happy, and that's the one. So I pick happy. Makes sense, right? But hello, how are, happy doesn't really make a lot of sense. So I'm wondering if somebody can suggest just something slightly better than this. Anybody wants to shoot an idea of how you would make this very simple model of picking one word slightly better? See on the chat or anybody suggest something. Exactly. Good answer. Yeah, and Tunji says 2 words. Yeah, so let's go for 3, for example. Let's say I go for 3 words. So I say, hello, how are? And I look at all the places in the text, in the huge data that I have, where the words hello, how are appear. So hello, how are things? And then I say, well, things is the most common word. So it's getting a little better, right? But I don't know if you've ever tried this. If you ever go on WhatsApp and start pressing the middle button that suggests the next word and seeing what you get pretty nonsensical stuff. Hello, how are you feeling this weekend? Your kind wishes for a wonderful weekend with your kindness and happiness for your family, love, and your kindness. Makes no sense, right? A few sets of words do make sense, right? Hello, how are you feeling? Kindness and happiness for your, a few words together work, but there's no way to keep a context of the whole thing. So we're not there yet in terms of our little algorithms that we're using here. But the idea is to get closer and closer to adding context to the thing. So in the same way that we went from 1 word and then 2 words and then 3 words, why don't we try a lot of words? what about like 10 words? You know, you have, hello, today I would like to inform you that blank. And so you look in the text of all the times that, hello, I would like to inform you that, and the next word more common is the, so we put the. What's a little drawback with this? Well, that 10 words may not appear. It's very unlikely. There's two sets of words that may just never appear. If I say the other day I was walking and 5 unicorns said, maybe there's just no way to finish that sentence because it never appears in the database. So we need something more advanced, right? We need something more advanced that captures context with all the words, but that doesn't force it to the particular words. Instead, something that just kind of maybe thinks a little bit, right? And so now we start getting to machine learning. We're getting to things like sentiment analysis. So if you've seen sentiment analysis or not, it's a classification thing. And it basically is a way to train a model to tell you if sentences are happy or sad. So for example, I am very happy is a happy sentence, and today was awful is a sad sentence. And the idea is that we have a data set of many sentences and label if they're happy or sad. We have a happy face or a sad face for all of them. And I have a question for you. How would you train one of these sentiment analysis models? So like, how would you, taking the data on the right, be able to figure out how to get, how to tell if new sentences are happy or sad? Wondering if there's any idea. Anybody wants to hop in and give me an idea? It can be on microphone or on the chat. How would you get the computer to look at these sentences in the left and be like, oh yeah, one is happy, one is sad? Well, people, if a negative word exists in a sentence, very good, I read it. We want to have positive and negative words, right? Like we want to try to find out what words are positive and negative. Maybe even more, we want to give points to them. Like let's say positive points to the positive words and negative points to the negative words, and based on the data. And then if you get a sentence that says, for example, I am very happy, then you add the points and it's the positive sentiment because it has the word happy, which has positive points. So it's 3, so it's happy. And this one says I had a very bad day. Well, it's there's a negative word. So bad day. And that is a bad one, right? So I see some good solutions. This one says label them. Yeah, absolutely. You have to label each of the words. Now the question is, how do we come up with this, right? How we come up with points for all the words? Well, we could, as a team, I would say, okay, Teju gets the letter A and Roy gets the letter B and I take the letter C and Jay gets the letter D, and we just go through the dictionary and label the words as happy or sad and put points if it's a very happy word, put points, etc. That's very tedious, and it only, you can make it, you want to make it work in many languages, you want to make it work sort of automatically. So that's where we use machine learning. So what we do is we want to have basically all the possible words and have them labeled. And pretty much what you can do is just basically go through sentences. And if you have a sentence where the words are where the sentiment is happy, then you add a little bit to all those words. And if the sentiment is sad, then you subtract a little bit. And that's pretty much the idea of training a model, right? Like you go through the data sets and see if sentences are happy or sad, and those words get shifted higher scores or lower scores depending on if the sentence is happy or sad. And maybe the words appear in both, but they will appear more on sentences that, if it's a happy word, it will appear more times on a happy sentence than on a sad sentence. So this is actually a neural network, a very simple neural network, and it's gonna look like this. So let's say that I'm gonna put all the words from I'm going to say that the first word is A in aardvark and the last one is zygote in the dictionary. And I'm going to put all of them and the score of each word in the edge corresponding to it. And for example, if I have the sentence I am happy, I'm going to put a 1 in the positions of the words I am and happy, and then I'm going to add the edges, right, times the 1 times each edge, and I get 3.2 plus 0.1 minus 0.2, because 3.2 is the score of the happy word, and that gives me 3.1. So I then conclude that the word the sentence I am happy is the happy sentence because it has a positive score. So that's pretty much a neural network. That's a neural network of one neuron. However, this obviously doesn't work perfectly. Right? This actually works really well for simple sentences, but it doesn't work perfectly. And the reason is that languages are just a lot more complex than adding and subtracting words. You can have sarcasm, you can have different meanings, you can have different orders, you can have a lot of things. And so a solution to this is to get into neural networks. And so neural networks are just a lot more of these. So here's one neuron, right? Which is scoring for every word that we add, just like before. And that's also called a perception. Okay, so a perception is the basic unit of a neural network, just like a neuron is the basic unit of a brain. And it kind of works like that, like it gets information from here from all the words, and then it outputs a 1 or a 0 if it's happy or sad. So like a neuron, like it gets synapses and outputs something, right? However, this is how I like to imagine them. So bear with me. This is how I imagine neural networks in a slightly philosophical way. Maybe happiness and sadness is just a complicated concept, and it's just not easy to model with just words. But maybe there are simpler concepts that you're more able to model with just words. For example, let's say if you have free time, that's one, or if you have family, or if you have friends. Let's say those three are simpler concepts, and you're more able to tell if you're talking about having friends with just simple scorings of the word. And then maybe out of the answers of these three, if you have free time and family and friends, then you can get the answers for happy and sad, right? And in reality, and that's a neural network where the outputs of this second layer of neurons goes into a third one that is just a more complex, more complicated in concept. And maybe you just have something like this, where the first layer is a bunch of neurons that tell you if you have rest, if you have family, if you have friends, food, or money. And then all those outputs go into a next layer, which tells you more complex things like emotional stability or health or purpose. And then that one goes to the end one that tells you if you're happy or sad. And you can have many layers, where each layer kind of takes care of a more complicated set of concepts that are just harder to model. And the first layer is just really simple stuff. And then the last one you get, if the sentence is happy or sad. So that's kind of how I imagine. Of course, you can get the computer to train this by itself in the same way that we find the scores of the words by going over the data set. And the computer will not come up with these things, but it'll come up with random things that maybe we can interpret or maybe we can't. But the fact is that this is a neural network. Basically, there's scores on each one of these edges, and every one of the little brain cells calculates the scores and outputs a 1 or a 0 if there's a yes or no for that concept. And then the next layer grabs what came out of the previous one, and so on and so forth, until the very last one says, are you happy or sad? Is this clear? Feel free to ask in the chat if something is made no sense or anything like that. Feel free to ask at any moment. But this is the idea, and this is kind of how I picture a neural network. Now, why did I start doing sentiment analysis if we're talking about finding the next word in a sentence? And the reason is because we're getting it, okay? So what are applications of sentiment analysis? And maybe somebody can help me on the chat. Like what would be, if you had a neural network that could tell you if sentences are, for example, happy or sad, like where would you use it? Where would you use these tools, this wonderful tool? Like see what the audience said. On customer reviews, very good. Very good, Cindy. You kind of get what I was gonna say. So customer reviews, yeah, if for example, if you chat with a representative, yeah, you're able to say if the chat was happy or if it was sad. Then there's yeah, brand monitoring, very well one. Healthcare, absolutely. Anything that requires checking if things are yes or no. You don't have to just say happy or sad, right? It can be emails, for example, spam or no spam. To train it to detect spam or no spam instead of happy or sad sentences, it's gonna find what spam, what words are spammy. Yes, very good. Financial analysis also would work. In healthcare, watch out, somebody's annotating in the in the chat in the sorry, give me 1 second. Okay. Yeah, so for example, spam detection, email classification, as Lukman suggested, for example, healthcare, you can check if a certain set of symptoms means the patient is happy or sad, you know, like it can be any of that. Let me pause and read this line. 1 second. Okay, so email classification is another one, right? Because I don't need to have just 2 answers, happy or sad, right? I can have 4 answers or 10 answers. I could classify the email into when you go to Gmail and it puts important, foreign, social, promotions, etc., personal, all that. And given the fact that I can actually answer more than a question of 2 things, I can actually answer a lot of out of a lot of things. So, for example, I can use a neural network to actually guess the next word in a sentence. So, for example, here's the neural network that will guess if your email would be out of 3 things: personal email, work email, or invitation. See, now I don't have 2 outputs, yes or no, happy, sad. I have 3: personal email, work email, and invitation. And if I make the last layer really big, then I can actually predict the next word, because this will output a score for every word. And the highest score, if I enter how are, then it will say the highest score would be 1. So I can use a neural network to guess the next word in a sentence, right? Does that make sense? So stop me, ask me any questions if it doesn't make sense. But the idea is that, and this is how it worked a while ago. This is how you would have how things would have predicted the next word in the models a few years ago, which is using that type of neural network. So how actually the transformer model work? Well, they pretty much do that. They predict the next word. So you go, hello, how, and then it says are. And then, for example, let's say you write something more complicated. You have write a story. So the neural network would just go, okay, the next word after write a story is once, because the story starts with the word once. And now how does it predict the next word? Well, now you input write a story once, and then it says, okay, the next one is upon. And how do you get the next word? Well, it goes, let's say how write a story once upon, what's the next word? So it predicts and it just keeps going word by word. And actually I found that hard to believe. I found it hard to believe that transformers build these wonderful pieces of text, write stories, write paragraphs, essays, tell you about anything you want, word by word. Because I mean, that's not how humans think. We don't think word by word. We formulate the thought and then put it in words. But transformers somehow, word by word, start creating stuff. But then what's the difference, right? Because neural networks are good at guessing the next word, but when you ask them something complicated, they're not able to tell you a story. They're not able to carry context. And so what transformers do is they do this well. So transformers can fill in one word at a time, but they do it really well. So I imagine a neural network like a truck, you know, that gets you somewhere. and a transformer like a very, very enhanced truck that has just a lot of superpowers. And so that's kind of how we're going to build a transformer. So a neural network, you know, as you saw before, it has a lot of layers. The layers are called feed forward. And a transformer is not more than a neural network with a lot of padding on the side and rockets here and like a bunch of boosters and things like that that help it work really well. But in the heart of it, you see the blue part. The blue part is a neural network. So it's a neural network with a lot of stuff. So today I'm going to tell you the structure of a transformer. And long story short, this is the image of the structure of a transformer. There's a couple more things, but the bulk is here, and I'm just gonna go over the whole thing. So you start on the left, you say write a story, that's the input, and it goes through a lot of stuff, and at the end that says one, that's the next word. So let's go through all these. Let's go through, for example, the first one, tokenization. That's kind of the simplest one. So you go. It just takes it has a bunch of hundreds of thousands of tokens, one corresponding to every word, one corresponding to every punctuation sign, etc. And it just kind of takes the words and puts them into these predefined tokens. This is just a pre-processing step. So that was easy. Then comes the embedding. So let me make a humongous deal about embeddings, because embeddings are the most important thing, I would say, in my opinion, the most important thing in large language models are embeddings. And why are they the most important thing? Because they are where the rubber meets the road, right? They are where the language starts becoming part of where the computer starts talking. Because humans, we speak in words, right? And computers speak in numbers. And you need a bridge between them. And the better this bridge is, the better language models we can have. And that's what an embedding. Basically, you cannot put, you know, the more effort we put in embeddings, the better everything's going to be. If tomorrow an embedding that's 10 times better than the best embedding comes in, all of a sudden language models are going to be a lot better. Because the better this bridge is, the more we can, the more computers can talk, you know. And an embedding is simply you take the language and turn it into numbers in the most effective possible way. What do I mean by the most effective possible way? Quiz one. So here's an embedding where every word, so you have the words, you know, football, basketball, baseball, truck, bicycle, banana, castle, etc. And all of them have two numbers assigned to them. By the way, I'm repeating, JJ introduced this a little bit ago, so I'm repeating some of his content. So thanks, JJ, for opening up the topic. So here we have two numbers for each word, right? The horizontal coordinate and the vertical coordinate. So banana, for example, 6.5. So here's a question: where would you put the word apple? And I'm going to give you three options. There's A, there's B, and there's C. So I'd love to hear from the audience. Where would you put the word apple in this embedding? A, B, or C? The C. Yeah. There's a B. It could be B, but I'm gonna go with the majority, which is C. So very good. I would put it in C as well. And why would it put it in C? The reason is because the embeddings have a particular property, which is that if you have words that are similar, then they are located in a close position. So for example, I would put it in 5.5, because 5.5 is where exactly as what it says, it says have the fruits. So the apple to go around the fruits, and maybe not so much in the houses or vehicles or sports. And so that's where I would put it, anywhere close to the fruits. So the numbers that I would assign to apple is 5, 5. Okay, slightly harder quiz. Where would you put the word cow? So we have the word cow, a baby cow, then we have the word puppy, a baby dog, and then the word dog. And the question is, would you put the word cow here, here, or here? A, B, or C? Let's see what the audience says. The word cow would go like here in A, a C, another A, another C, B, C, C, A. So I think C is winning by a little bit, but it's close call. It is a close call because it could go close to cow because it's a similar type of animal. It could go close to dog because it's an adult animal. But however, I put it in C. And I'll tell you why I would put it in C, because these embeddings have structure, right? And so, for example, the way I like to see it is with analogies, right? There's an analogy that says that a puppy is to a dog like a cow is to a cow, because a puppy is a baby dog and a cow is a baby cow, right? So that's an analogy. It's given by these two arrows. And you can also have this analogy of saying a puppy is to a cow as a dog is to a cow, because it's the baby animal to the other baby animal and the adult animal to the other adult animal. However, the way to look at it is the sort of language math, because embedding kind of capture the concept of words. If you look at this, if you move towards the right, you go from baby animal to adult animal, right? So like an old dog would go a little further on this to the right. And this one, the vertical one, measures size, right? Because I'm going from a small animal to a big animal, like a whale would be way up, right? So these two axes or the two numbers actually mean something. One of them means the age and the other one means the size. And so I have basically low number for age, low number for size, a puppy, etc., etc. And that's an embedding with two numbers, right? The street and the avenue, the number of the horizontal coordinate and the vertical coordinate. And if we were to have more, obviously more columns, then I would just add dimensions here. So I would have, for example, instead of having in the plane, I would just have the points flying in 3D, right? The points flying in 3D would be the embedding, right? So the embedding, I always like to imagine it as like the words are in some space. If it's 4 numbers, then I can imagine a 4-dimensional space. But if I picture it in my head, there can be points all over the place flying, and the words are close, like apple is here and then orange is here, and so on. And in reality, the embeddings that we use don't have 2 numbers, but they have lots of them. So one embedding we have at Cohere has 4,096 numbers. So 4,096 numbers for each word. That's a huge amount of information per word, right? And just like you saw before, that one was the size and the age. Each column kind of means something. It could be the size, the color, etc. But since these are built in a machine learning way by neural networks, not by humans, where we don't go around adding putting numbers, then sometimes there are properties that we can't read, that we cannot identify, but the computer can. And there may be combinations of properties or something we haven't seen, or maybe size, and that's what embeddings are. So imagine a huge description of each word in a bunch of columns, and obviously similar words have similar descriptions, so they have similar numbers, right? So the most imagine doing the best possible job at assigning 4,096 numbers to each word. That's an embedding. And it doesn't just work with words, it also works with sentences, right? You can have, for example, for each sentence, you can throw in an embedding and get 4,096 numbers. And the sentences that may not have words in common, but that have similar meaning, are going to have similar embeddings. Here's an example. I was playing with the Cohere playground, and there's a bunch of sentences that all talk about kind of airports. And if you look at some, and on the right, I have, there's 4,096 numbers, but I just pick the first 10 and I plot them with colors. So basically, lighter are the lower colors and darker are the higher numbers, and darker are the higher numbers. And if you look at sentences that are similar, for example, show me a list of ground transportation at Boston Airport and show me Boston ground transportation, they have very similar embedding because the numbers are very similar. And this one too, what ground transportation is made in Boston? Similar number. You can see those rows look similar. Also, you can play with in the same playground that I'll show you later. You can actually put a bunch of words, sentences, and it puts similar sentences together. These were about hello, how's it going? These are about a dog, and these were about watching football. So anyway, those are the embeddings, and the multilingual embeddings, which you will be seeing a lot this week, are basically the same thing, except they're language agnostic. So you can put a sentence in any language. There's 100 and almost 110 languages. You can put a sentence in any language, and it's going to put it close to the same sentence in all the other languages. So for example, if I have English, French, and Spanish, and I have the same sentence, and all the sentences with bear appear around here, all the ones with football appear here, the ones with fruits appear, the apple appears here, and the ones with the sky appear here. So these multilingual embeddings are really powerful because, for example, you can train a model in one language and then make it decide sentiment analysis, and then make it classify things in another language without seeing it, just by using the embedding, because you're turning all the languages into the same number or similar numbers, and the computer speaks numbers. So it basically makes everything language agnostic, and then that's why we're so excited about these models and what you can do with this multilingual model, right? Quick stop for questions. Are there any questions that you may have? So feel free to put them in the chat. I can continue, but feel free to ask in the chat, and I'll stop and answer them. Here's a question: how do we build this embedding? Right? Do we get a crew of people and a huge page of 4,096 columns and start just adding numbers and hope that they work? Well, no, that's not right. We're going to actually use neural networks to build this embedding. So check it out. We're going to use them in a slightly complicated way. Actually, let me give you a mental image of how I imagine this embedding. Okay, just picture the following. Let's say that you're going to put a lot of sensors in my brain, so that a bunch of numbers show up in the screen. Okay, just the amount of brain activity in a bunch of different places. And then what you do is you show me things and then read the numbers that appear. So for example, if you show me an apple, that activates a bunch of things in my brain and you see a bunch of numbers. Then you show me an orange and it activates a bunch of things in my brain and shows a bunch of numbers. They're probably similar. An apple gives me similar sensations than an orange. But if you put like a truck, then different numbers come out because that activates different parts of my brain, right? That's a twisted way to find an embedding, right? You just show me every word and look at the numbers in the screen, and that turns words into numbers in a way that makes sense, because I would have similar reactions to similar things. Well, we can't really use someone's brain, but a neural network is like a brain, so we can use that. So what we do is we take a big neural network that guesses the next word in a sentence, and we input one word, and then we look at what numbers come out of the last layer of the neural network. Okay, what numbers came out of there? Remember that these layers know a lot about the word. And so whatever numbers come out of that layer, that's the numbers we're going to use for the embedding of Apple. And that works really well, because if I were to put an orange, well, you would imagine that similar words, similar numbers come out, because the neural network behaves similar with the word apple and with the word orange, right? So it's kind of a hacky way to get embeddings, but it works really well. It's called word to vec. And there's a bunch of different ways to get embeddings, but this was kind of my favorite because it's so indirect, right? Okay, so we have our embedding, and our embedding takes every word and turns it into a huge list of numbers. So write a story, period. Every token has an embedding. So now we have all the way to embedding. We have tokenization, turns it into tokens, and embedding turns the word into numbers. Again, stop me if there's any questions. Now we have positional encoding. Positional encoding is it basically adds order to the word. So let's say I have the sentences, I'm not sad, I'm happy, and the sentences, I'm not happy and sad. These have the same embedding vectors because I turn the same word into vectors, right? So the question is, how do we sort of disorganize them so that they give us different things? And the way is it's kind of simple and it really just kind of works, which is that I take a different vector for the first sentence, for the first word, the second word, etc., and I just add that vector to the first word and the second vector to the second word, etc. And these blue numbers are different, and they have cosines and sines in a way that's kind of grow in a way that makes sense. And that's what you use to have the organized words. So you basically add a little thing to the first word, to the second word, to the third word that's different, so that you get a different vector. It doesn't really matter what you add, but as long as it's the same thing, like a bunch of different things have been tried, and some of them work better than others. It's really more of a thing of it working than it making a ton of sense. But that's the positional encoding. So now that we've tokenized, we've embedded, turning into numbers, and we've encoded with position, we have a bunch of vectors a bunch of numbers that come into the neural network. And so now I'm going to explain you the series of transformer blocks. So that has two things, attention and feed forward. So let me tell you what attention is. Attention is one of my favorite things, and it's really what started this development of large language models. They started with a paper called "Attention is All You Need," which actually had the first architecture of a transformer. And how does attention work? Well, attention deals with the following problem. Let's say that I have two sentences: the bank of the river and money in the bank. So there's the word bank that we as humans know it can be used in different ways, right? The bank of the river is this little piece of land right by the river, something in nature. And money in the bank, this bank is the institution that holds money. But how do we know as humans that the bank of the bank in the left sentence is different than the bank in the right sentence? We use context, right? So in particular here, the word river is the one that hints that the bank we're talking about is in nature. And the word money here is the one that hints that the bank we're talking about is an institution with money. Now, how do we tell the computer to use the other words around to sort of modify the word bank? Like, I like to see this like gravity. Okay, imagine that this is space. Okay, and here you have the Earth and the Moon, and the Earth and the Moon kind of pull each other together because they're close by, right? So let's just think of the Earth. Let's think everything else is fixed, and let's think of the Earth. So the Moon kind of pulls the Earth towards it because it's close, whereas the other planets are so far away that they don't really pull the Earth that much. They pull it very little, okay? So if we fix everything else, the Earth would kind of move here towards it, right? Why did I digress with gravity? Because the same thing happens with words. Imagine that here's an embedding, right? Maybe 2-dimensional, maybe 4096 dimensions or something. But the fact that there's a huge space where these words are flying around, and the words money and bank are close by, and the word in is somewhere there in Andromeda, and the word day is far away in a different galaxy because they're not that related. And if you take the word bank, then it gets pulled by the word money a lot, and not very much by the words in and there. So therefore, the word bank will move a little bit towards money. And that's attention. You move towards the words in your sentence. So the word bank here, let's say that you have all the words of all the finance words in this part of the universe and all the nature words in this part of the universe. and the word bank is here kind of confused, not knowing where it belongs. But we're gonna have different words with bank. For the sentence money in the bank, we're gonna take bank and move it towards the word money that gets pulled. And that gives us a new word bank with new coordinates. And that new word with new coordinates is the one that we're gonna use for the word bank. So whatever numbers the black bank has are not the ones we're gonna use. We're gonna use the numbers that the red bank has. We moved it a little bit. And then likewise for the bank of the river, we're gonna get bank and pull it by the word river. And now that gives us new coordinates for the word bank. And the green bank is the one we're gonna use. Those coordinates are the one we're gonna use for the sentence, the bank of the river, and not the coordinates of the original bank. Does that make sense? Let me know if anything is not clear, and I'll repeat it. But the idea is that we sort of pull the words together in the same sentence or in the same paragraph so that they start getting closer and closer to each other and giving each other context. Okay. So basically, attention, just take sentence money in the bank, where bank, the computer has no idea what embedding to use for bank. And then it really gives it a context. And now it has a much better numbers for the word bank. And if you read the paper, you'll see something called multi-head attention. It just means doing this several times. So you have a bunch of different embeddings, and in each one you do attention, and then you join them in a way that's kind of a machine learning way. But imagine doing this several times. That's multi-headed attention. All right. So we're almost done because we went through tokenization, embedding, positional encoding, and attention. And then there's feed forward, but feed forward is just a neural network. So feed forward is just the good old neural network that guesses the next word. So basically this neural network that guesses the next word. And these layers are gonna call feed forward. And all we have to do is we're gonna put attention layers sort of in between. We're gonna sandwich part of the neural network attention layers and just put it in transformer blocks like that and put many of these blocks. So you're always sort of doing a layer of neural network and then gravitating to get the attention, the context, and continuing this way for many blocks. And that's what the series of transformer blocks does. And then finally, the softmax, which is sort of an easier step. It really just gives you some probability. So when the transformer outputs stuff, it outputs a bunch of scores, a bunch of numbers for each one of the words. And the higher the score, the more likely that the word appears as the next word. But we don't want to just pick the highest score, because then the transformer will always be outputting the exact same thing. We don't want to ask the transformer the same thing and get the exact same answer. We want some probabilistic thing, something that's very likely to be the good answer, but the words it differently, like a human would do, right? Like we just word it differently every time you get asked the same question. And so we have a softmax layer, which turns all these scores into probabilities. Now, if you know the softmax, the numbers are wrong, but I'm just putting them there. But basically, it turns high numbers into high probabilities and low numbers into low probabilities in a way that they add to 1. And then it picks out of that probability. So for example, it picks the word once with 0.5 probability, the word in with 0.2 probability, and word there with 0.3 probability. And so sometimes it'll pick once, but sometimes it's going to pick in or there or something else, right? But it's always going to pick one that's likely to be the next. And that's the architecture of a transformer. So let's just do a little recap. Well, tokenization is easy. Embedding turns words into numbers. Positional encoding gives the words order. The attention gives the words context. So that words that can be used in 2 different ways, the model knows which one you're using. And the feed forward is the neural network used to guess the next word. And the softmax is the one that assigns the probabilities in order to get the output. That's the structure of a transformer, give or take some small details. Any questions about this? So structure-wise, we're done. Now, as you can imagine, this has no reason to work so well, right? Because now the problem is not the model, but the data, right? Like, so who can tell me potential problems that this transformer may have if you were to just leave it out in the wilderness and let it answer stuff? Any idea of potential problem? And so while people write them down, I will also say some, but feel free to continue inputting. Let's say, well, this is where post-training comes in. The transformers are trained on the entire internet. And as you know, the internet is not a very well organized repository of information. It's got everything. And so if you train them all on everything, it's just gonna, random stuff will come out. For example, let's say I tell the transformer to write me a story. Well, the internet's not, it's not a question answering thing, right? Oh, I see an answer. It says needs large vocabulary dictionary to get context. Absolutely, it needs huge data sets to be trained. And in particular, yeah, you can take pretty much the entire internet to train it. But here's the problem. What does the internet say if you say write a story? What's normally the next thing that comes in? Sometimes it's the story, but sometimes maybe you have an exam, right? And the exam has question 1, write a story. Question 2, write a poem. Question 3, write an essay, etc. And so it may answer write a poem, right? It could be that you say, what's the capital of Nigeria? And the answer is, what's the capital of Rwanda? Because it's just an exam that, the next question is another question. So what do you do to solve this? It's actually post training. You do things with the data, not with the model. You have a lot of questions. You curate a lot of questions and the correct answers, and then train it with those so that it starts learning that when you get a question, you're supposed to answer it and not ask something else that's similar or something like that. So you get, you create huge data sets with lots of information of different things. And that's actually the hard part, I would say, that of actually getting humans to write these things or finding the right places in order to post-train. Here's another problem that can happen. Let's say that I'm asking it a question. Let's say I'm chatting with this, right? Like, well, what's happening in Nigeria? And it goes to Abuja. And then I continue talking to it. Oh, cool. And it goes, yeah. And then I go, since what year? And it has no idea what I'm talking about, because it doesn't associate the question with something that happened 3 or 4 lines above, because they have no reason to do it, right? If you train something to answer what's the most likely thing that will come after based on the data of the internet, there's no reason it has to remember what you told it before. So what solution here is to just train it with a lot of chat data sets of long chat, so that it starts kind of capturing the idea that you have to remember a few things before. So this part gets a little philosophical, but the idea is that what the data you give it is how it behaves. And these models are so big and have so many, like, billions of parameters that they somehow start capturing behaviors like that. And so in particular, if you have some specialized data, you can put it there. So if you have your own company or your own foundation or your own course or your library or anything, you can put that data and post-train the transformer. And just like a human that would sort of remember the latest stuff more than the previous stuff, and just get trained to answer your question. So that's pretty much how transformers work. I think we're doing okay with time, but Teju, let me know. This is this is some links. I would love for you to join the Discord community. Feel free to put the feel free to put your phone in and get the QR code to join the Discord community and try the models. If I have time, I can give you a little demo of the models. But Teju, let me know if we're if we're good with time, or if we go to question answers. And in the meantime, here's the Cohere playground, and here are some of my coordinates. So if you like this, I have a lot of talks. I have a lot of machine learning videos on YouTube, so check out Serrano.academy. And I have a page with my blog, Serrano.academy. There's my Twitter, Louis Likes Math. And I have a book called Rocking Machine Learning, which if you want to take a picture of this or something, if you I can send a link in the chat, but there's a 40% discount code with that code if you're interested. So I'll leave this there, and in the meantime, I'm happy to answer any questions. By the way, Teju, how much time do we have for questions to see if I demo the
Hi, Louis. I think you can. Thank you so much for the talk. I think you can give a demo if you'd like. We still have some time, and you can also open it up for questions.
Let's do both because I have time for both. If you go, you see my screen, right? If you go to dashboard cohere.ai, you may have to log in using Google or a few options, and then you go to playground, and then you have the endpoints that are generate, classify, embed, and summarize. So let me quickly show them. Generate is the one that just you ask it something and it tells you, right? So you have, for example, write 5 titles for blog ideas for the keywords large language model or text generation, and it just goes, so for example, write a paragraph describing an AI hackathon, and it just kind of gives it to you. So it's the usual like ChatGPT style thing, right? Then there's classify, which actually, classify it's like sentiment analysis, which is an old thing, but the cool thing of this is that the embedding is very strong. And so therefore, you, with just a few examples, like 3, 4, or 5 of each one of these, you can actually train the model pretty well. So let me give you a bigger example. Product review sentiment. No, not this one. Fintech email classifier. So you have different types of emails and about 5 examples for each one. And with that, you can actually classify stuff. Oh no, I think it's broken. Oh, what did I do here? Let me see. Okay, it's not working, but the fact is it does classify stuff with a few examples. Then there's embed, which is the embedding that I was telling you. So for example, we can look at subreddit titles. There's a lot of titles of Reddit articles. And when I go embed, what it does is it puts them here. This is a 2-dimensional embedding, but in the Cohere embedding, if you use an encode, it'll give you the thousands of length of numbers, but here this one gives you 2. And as you can see, it puts similar things close by, right? This is talking about work, food deliveries. This one's over here talking about the Queen. This one's over here about housing, and so on, right? It's about relationships and so on. So it this embedding just is really, really good for like sentences, and it puts them into vectors. And finally, summarize. So let's do something. Let me just take the Cohere AI hack page and copy it and put it here on summarize. And then I'm just gonna say length long and format paragraph. I think that's the one. And then I go run. And then it summarizes. So it tells, a summary. They have some parameters like temperature. So for example, low temperature is kind of like, it's not very creative. It's more like rigid. High temperature gets very creative. It may lead to saying crazy things, but it also is going to be more imaginative, as you can see, right? And I think that's the end. And so I'm happy to answer any questions. Yes, Murak.
Okay, thank you so much, Liz. I think it has been a wonderful session. You have done justice to it. Yeah. So I have two questions actually for the community, not just for myself. So the
Sure.
first one is, I know the hackathon will require the participant to use the data for their own project. So if the participant on their own to find the data and train and do the embeddings themselves, or Cohere is going to provide the data for the embedding. Also,
Yeah.
to use the Cohere multilingual embedding, does the participant need to get the Cohere credits before they could be able to use the multilingual embedding? Those are my two
Yes,
questions.
you need the credits for that. Actually, yeah, is Roy here? Because he would know more about that, about those details.
I can also jump in.
Or Teju, yes.
Yes, there is a free tier that everyone can try out. So you can go to cohere.com. We also put it on the resource page, and just sign up. You get a free credit, and you can already use that to start building. And I don't think from my conversation with Roy, you're not going to run out of that credit for the hackathon. So it's available for the community to use to test out their ideas. And so that's about the credit.
Thank you. Awesome. Any other questions? All right. Well, thank you very much. I think I'll pass the baton back to Teju. Thanks for your attention.
Thank you very much, Louise. Thank you for everyone that is on the call, and see you tomorrow.